let us introduce ourselves to what are called classes. So, this is something that we have learnt already, that a set of elements is called a group if and only if they satisfy these 4 properties: closure, presence of identity element, associativity and reciprocity, right. Is commutativity an essential criterion? No. If commutativity holds, then we call it an abelian group. And what we learnt yesterday is that cyclic groups are always abelian groups. What is a cyclic group? A cyclic group is like this. Let us say element A is something x, then B is x square, C is x cube, and so on and so forth. We are going to look at an example of an actual cyclic group a little later today. Okay. And this is something that we have discussed also, group multiplication tables. We have said that a group multiplication table of a group of H1 is trivial. A group of H1 itself is trivial, like a very lonesome man, right, the group by himself. Group of 2, a little more interesting, E and A, that's very easy. Group of 3, EAB, we found that it's a cyclic group and it's an abelian group. Okay. What would be an example from our point groups of a cyclic group of order 3? C3, C3, C3 square and E equal to C3 cube. Okay. So, the point is, if you work out the multiplication table of C3, replace A by C3 and B by C3 square, then you are going to get a multiplication table that looks like this. This will be C3, this will be C3 square, this will be C3, C3 square, C3 square, C3. That then would be the multiplication table of something like C3. Alright. And we have talked about something like something called rearrangement theorem. So, what rearrangement theorem tells us is that in a given row or in a given column, the same element will not be repeated twice, right. So, every row and every column is really a rearrangement of the possibilities, okay. And that is what helps us build the group multiplication table in the first place. Without rearrangement theorem, we cannot really build the group multiplication table, alright. Now, I think we had stopped here yesterday, H equal to 4. Let us now do a little bit of Sudoku and work out the group multiplication table of H equal to 4. For your benefit, I have written the first row and the first column. So, the pillars are there, you need to do the brickwork. How do you do the brickwork? Before you proceed, let me tell you there are 2 possibilities. One possibility is that it is a cyclic group and the other possibility is that it is not a cyclic group, right. Somehow I do not know really why, but I went with in the reverse order compared to what is there in Cotton's book, and since Cotton is not teaching the class, I am, we will go by my order, and it does not matter which one is 1, which one is 2. So, let us say that case 1 is the case where every element is its own inverse. Will that work? Will that not work? We will see. Is it possible to construct a multiplication table using A equal to A inverse, B equal to B inverse, C equal to C inverse? Let us see. So, let us fill it in. Where will I write the E's then? Diagonally. Diagonal elements are all E, right. And just to remember that we are working with group number 1, I call it G4 1, okay, G4 then superscript 1 in bracket. So, these will be the E's, right. Now let us try to fill in. See, will you agree with me if I write C here? Why? Because in the group you have A already, so your options are B and C, but you cannot write B because B is there in the column. So, there is no option but to write C. So, what will be this element here? B. B is the only one that is missing. AECB. Next, we can go with this or this. Here, since the last column has only one vacancy, it's easier to fill in. What will it be? A. Very simple. So now, once again, in the third row, only one vacancy is there. What will it be? C. So now, what will the other two elements be? Simple. So we have been able to construct a group multiplication table considering that each element is an inverse of itself. Alright. So it has worked out. Is this a cyclic group? Yes or no? I don't think it's a cyclic group. Let us now try to work out the character table for a cyclic group if it is possible. What is the definition of cyclic group? A equal to x, b equal to x square, c equal to x cube, and e will be equal to x to the power 4. Okay. What would be an example? C4 once again. Fine. So now knowing this, we can fill it in. What is the inverse of what? What is the inverse of x? A. If it's a cyclic group, A equal to x, b equal to x square, c equal to x cube, and e equal to x to the power 4. Then what is the inverse of A? C. And what is the inverse of C? Better be A. What is the inverse of B? There is no other choice. And besides, if you look at this, x square into x square is x to the power 4, which is E. Right? So A equal to C inverse, C equal to A inverse, and B is the inverse of itself. Alright? So now can we fill in? Where will the E's be? This will be the E's, because A is C inverse and C is A inverse. So CA and AC will be E, and BB, B square, should also be E, right? And now see, it is very easy to fill in. You don't really need rearrangement theorem anymore, because I have imposed an additional condition that it is a cyclic group. Okay, so you can work out yourself. So this, what is this? What will this be? A square? A square will be x square, that is B. What is BA? Oh, you could have filled that using the rearrangement theorem also, isn't it? What do I call this? Do I call this BA or AB? This element here, do I call this BA or AB? You could call it anything, right? But the convention is that top first, side next. Okay? The name of the column first, the name of the row after that. Alright? Please don't get confused here. Eventually you can build everything in whatever convention you want. But then if all of us go around building our own conventions, then we are going to create a Tower of Babel. You know Tower of Babel? What was the Tower of Babel? Who knows the story? Okay, Prabhu knows. Huh? Mehak, what is the Tower of Babel? Babel is a place, right? So there the people decided to build a tower which would be so tall that it would reach the heavens. Kind of like the stairs that Ravan apparently tried to build. So now when this was being built, those higher above saw that it's a very problematic issue. Man is going to reach the heaven. So to prevent that, God created languages. So everybody has started speaking a different language. Hebrew, Spanish, Hindi, Italian, Zulu, Ubuntu, and nobody understood what the other guy was saying. So that is why Tower of Babel is synonymous with a situation where everybody speaks a different language and nobody understands anything. Okay, so we don't want to do that. So let us go by a uniform convention, top first, side second. Okay, so this is BA. Let's come back to this. What will this be? What is AB? Well, you have worked out BA already, right? And this is an abelian group. So you know what AB is going to be. It's C. What about CV? A, B. So, we have constructed character tables for H equal to 4 for two different situations. One in which each element is the inverse of itself, and the other in which you have a cyclic group. There is no other possibility. There is no other possibility, because you see you already provided for whatever could have been done. Here everything is inverse of itself, here one is the inverse of the other, and the third chap is left out, it has to be the inverse of itself. Now, the only other possibility that you can think of perhaps is A equal to B inverse, but that is trivial, right? That is just using a different name. A, B, C are perfectly arbitrary labels at this point. Saying A equal to C inverse, B equal to B inverse, or saying A equal to B inverse, C equal to C inverse mean the same, right? There is no difference. So, these are the only two possibilities for H equal to 4. Okay? Satisfied? So, now what you could do is you could go on playing this Sudoku, and you could go on working out the multiplication tables of H equal to 5, 6, 7, and I will encourage you to work out at least 5, 6, 7, at least these three, because those who have taken my class know that I have this penchant for asking questions of the next step, things that I do not teach, right. So, maybe in the mid-sem I will ask you to work out the character table of H equal to 16. No, I will not do that. H equal to 16 will be kind of taking things a bit too far, but 5, 6, 7 is okay, alright. So, please work this out by yourself when you have nothing else to do. In any case, it is fun, right. People do Sudoku to pass time, you do this kind of Sudoku, what is the problem? Alright, fine. So, now let us do something, let us take examples of actual point groups. Eventually that is what we want to do, right. So, let us take two examples, one a cyclic group and the other, I do not know whether I should call it an acyclic group, and another group which is not cyclic. Yeah. So, C4 to start with, you wanted C4, C4, E, C4, C4 square, C4 cube. Actually, I had color coded the whole thing, but then I had goofed up, so the color is all gone. Anyway, can you fill this in without looking at here? What is it going to be? What is it likely to be? G4 1 or G4 2? It is a cyclic group. Cyclic group is G4 2 by my convention. In Cotton's book it is given as G4 1. They have handled the cyclic group first, but here as far as this slide is concerned, it is G4 2. Okay. Let us see if we get there or not. What will be the first row, first column? Very easy, right. Work out the second row. C4 C4 is C4 square, C4 square C4 is C4 cube. What is C4 cube? The last one, okay. C4 cube C4 is E, right, and similarly you can work out the second column also. C4 C4 square C4 cube, C4 C4 cube E, alright. What will be this element here? C4 square E, and C4 cube C4 square C4, right. C4 cube C4 square would be C4 to the power 5, that is C4 to the power 4 multiplied by C4. C4 to the power 4 is E, like 1. So, you get C4, right. Oh, we are done. What is left? Only one element, and you do not even have to work it out. Yeah, C4 square. So, now see, does it match G4 2 or not? So, that is like A, the green ones, this is green, right? Okay. Now, the blue ones are like B. Look at the pattern in G4 2, and orange ones are like C, right. So, we have got G4 2. We were expecting G4 2, we have got G4 2 using an actual example of a point group, alright. So, these two are not completely divorced from each other, they are one and the same, it is just that one is abstract and the other is something that is constructed using symmetry operations, alright. Let's take another example, 4 elements. Can you think of another point group which has 4 operations? Yes, good old C2V, right? We lose no chance of drawing the structure of water molecule, right? So let's see, and for your benefit, what I have done is here the color code is okay. So I have already written the first row and the first column and the E's. Just check, is this okay? E, C2 is E. What is the situation here? Every element, every operation is its own inverse, isn't it? C2 is its own inverse, sigma V is its own inverse, sigma V dash is its own inverse. So the E's are going to be along the diagonal, like G41. Got it? Okay. Now can we fill this in? Sigma V C2, what will it be? Sigma V G2, C2. No, don't cheat. Don't look at G41. Only think what will happen. What are my options? Sigma V C2. Sigma V means what? Deflection on the molecular plane, right? And then you apply a C2. So what will happen? HA and HB will interchange places. Now my problem is this, when HA and HB interchange places for 2 operations, not one. One is C2 and the other is sigma V dashed. Okay. So when I apply sigma V and sigma V and then C2, or C2 and sigma V, doesn't matter. What should I write? Should I write sigma V dashed or should I write C2? Why? What is identity relationship? Where is E? Sigma V C2. I'm talking about sigma V C2. Successive operations of sigma V C2 or C2 and sigma V, doesn't matter. Alright. So see this H1, H2, H3, H4, these are all just mathematics, right? And we are trying to apply them to chemical systems. So the logic from mathematics and logic from chemistry should match. So let us think of the logic from chemistry or logic of turning things, that's all. So what happens when I apply sigma V dashed? So what we said is that sigma V dashed as well as C2 cause an interchange between HA and HB, right? But still now if you look at it from, if you really nitpick, what you see is that their effects are not exactly the same. So as Okaprabha was saying, if you apply sigma V dashed, what happens? HA and HB interchange, right? But the upper lobe remains the upper lobe, isn't it? When you apply sigma V dashed, this is the upper lobe of HA, this is the upper lobe of HB. Upper lobe remains upper lobe, it's a deflection, right? Right? However, when you apply C2, then what happens? Upper lobe becomes lower lobe, isn't it? Not only do A and B change places, the upper lobe become the lower lobe. So sigma V dash and C2 are distinct operations. If you have some way of painting the upper lobe pink and painting the lower lobe blue, then you will see that their operations are different, their effects are different. Alright. Keeping that in mind, now can you tell me what will it be? Forget about the rearrangement theorem for the time being. Keeping just this upper lobe, lower lobe in mind, can you tell me what this should be? When you apply sigma V, what happens? Nothing happens. Is that right? Nothing happens? No. There is no change in position of the atoms, but upper lobes become lower lobes, isn't it? The lobe that was on top of the molecular plane goes below, the lobe that was below the molecular plane goes on top, right? HA remains HA, HB remains HB, but upper lobe, lower lobe interchange is there. Then when you apply C2, then what will happen? First of all, HA, HB will interchange, and upper lobe and lower lobe will also interchange. So what will you get? What is the net effect? Net effect is sigma v dashed, isn't it? AB have interchanged, but since upper lobe and lower lobe have interchanged twice, they are reset. So this is sigma v dashed and not C2. Not using rearrangement theorem, but just by thinking of the structure of the molecule and turning it around, we can convince ourselves that sigma v dashed is what should be there, not C2. Alright? Okay? The reason why I am spending so much time here is that it is very easy to use the rearrangement theorem, but then the two logics are not reconciled. The two ways of thinking are not reconciled. Okay, now they are. Are you okay so far? Can move ahead? Now I think you can, yeah. What do you think? Yes. Sigma v dash C2 is sigma v similarly, and then you can fill them in. Alright. And now you match the colors. Don't you, have you not reproduced the character table of G41? Right? So this is an example of G41, C2V, and C4 is an example of the cyclic group G42. Okay? Right? So math and science are going, math and chemistry are going hand in hand so far. No conflict so far. Good. Let's move ahead.